Alright, this is the 3.6 supplement if you're doing the Calculus BC course. If you're doing my AB course, I believe this corresponds to the section 6.4 supplement. And here we go. Now, all you've been doing so far in calculus is something called differential calculus. But there's actually another part which we call integral calculus. Just like how there was the main question in the differential part of calculus, aka find the slope of the tangent line, here the main question of integral calculus is, can you find the area between the graph of a function, which is some irregular shape, and the x-axis bounded by the starting value of x at a and the ending value of x at b. Okay? Now, let me show you a picture of what I mean. Let's say you got this crazy function. We'll call that function f of x. I want you to find the area between a and b. So if I were to carve this up, I want you to find this highlighted area here. And that is the main question of integral calculus. And if you're curious what type of symbol or notation is used to represent this area, it is the integral, or this little squiggly, I don't know, s, I guess you can say, the integral from a to b of the function f of x with the dx at the end. Okay? So, to help us understand this concept, I have an investigation for you today. Yes, and you're going to be a sleuth and try to figure this out. I want us to use the graph of y equals f of t equals 2t to evaluate the following integral. So meaning my crazy function now is this function y equals to 2t. Notice I changed the variable to t, and this is y, but the idea is the same. T is your independent variable. Okay? I'll show you why I had to choose t and not x in a moment. But if I were to graph this out, notice that I would have a point 0, 0. If I go 1 unit to the right of t, then I would go 2 units up, 2, and I'd be at 4, and 3, of course, we'd be at 6. So hopefully you'll see this nice straight line. That's my function y equals to 2t. Okay? Now, the reason I didn't use x was because x actually is my variable now. Okay? So what I want you to say is this capital F of x is equal to the integral from 0 to little x of the function f of t dt. Meaning capital F of x is the area, okay? Area under the curve, or in this case, the line, okay? You're starting at 0 and you're now ending at this value of x. So I can actually change where I end this region, okay? F of t is the function, so I replace that with 2t. So notice that the integral varies with the upper limit x. And then the integral really then is a function of x. Okay? And that's why we called it capital F of x. Now, let's visualize this. Remember, this is the area in the curve, so let's visualize this using geometric formulas. So here I go. If I said x is 0, meaning this ending value is 0, so I want you to really say this. This represents the integral from 0 to 0 of the function 2t dt. So if I went from 0 to 0, starting at 0, ending at 0, what is the area from 0 to 0? Please say 0. Yes. Okay, now let's do the next one. What if I said now the integral from 0 to 1 of 2t dt? So visually on the graph, this represents the area underneath the curve, between that curve and the x-axis, starting from 0 and ending at 1. And notice you have a nice right-angle triangle. How do I find the area of a triangle? Base times height divided by 2, so 1 times 2 divided by 2. And that, of course, equals to 1. Okay? Now, I want you to do the next one with you together, and then I want you to try the rest on your own. So here we go from 0 to 2 of 2t dt. And then if you look at my diagram now, I'm going to change it because I'm going to 2 now, which is a bigger triangle. But similarly, like before, it's the base, which is 2, times the height, which is 4, divided by 2, and the answer is 4. Okay? Please go ahead yourself and try to figure out 3 and then 4, and see if you can figure out what, in general, you get. Yes, do it yourself. Don't wait for me. Hopefully you see the base is 3, the height is 6, divided by 2, so the answer is 9. This would be 4 times, now the height would be 8, divided by 2, so that's 16. Now notice what our answers are for each of these. 0, 1, 4, 9, 16. And how is that related to x? Hopefully you can see that they are just the square. So in general, if I actually had this, you could hopefully see that the pattern says this is x squared. Now let me try to prove this to you, because really I'm going from 0 to x of 2t dt. And if I did go to x, let's just pretend x was like some weird number out here. Notice that the triangle that I'm creating is this. And how would I describe the base? That's x. How would I describe the height? Well, the height is 2 times t. My t value is x, so it's double that, 2x. So if I use the same kind of idea, it'd be the base times the height divided by 2. And that, of course, equals to, what, 2x squared over 2, which, of course, is just x squared, like what you predicted earlier. Okay? So, therefore, the integral, or the area underneath this curve of 2t dt, when you go from 0 to x, is really just the function x squared. Now, hopefully, you can kind of see a relationship between the little f of t and the capital F of x. Can you see what this was? 2t, right? And then x squared. Hopefully you can see that, hey, if I take the derivative of x squared, I'll get 2x, which is equivalent to 2t, if you think about it, and vice versa. So I want you to understand that this capital F of x function, that, not equals, is the antiderivative of the little function f of x, I guess in this case f of t, or I can say something like this: capital F of x is equal to the integral from 0 to little x of the function f of t dt. This area is really just the antiderivative. Wow. Now, for those of you in AB, that's it for the lesson, but if you want to continue, you can listen along. The BC students, yeah, I'm going to actually prove it to you, but the AB students, I didn't have time, so I didn't. But since you're watching this video, if you want to keep watching, please do. All right? So those of you who have the notes, you can turn the page, and I'm going to try to prove this to you now. Okay? And so to prove this, I want us to assume that there's some function, which I will call capital F of x, such that it will tell us the area under the curve between y equals f of x and the lines x equals to a and x equals to x. Now if you think about what I mean by that, it's this picture here. So capital F of x goes from a to x. So notice this capital F of x would be this region here, a to x. Okay, I'm going to draw it here again. Whee! I'm just going to draw it here so you can see it, a to x. Okay? Now, here's the question. What's capital F of x plus h? Well, capital F of x plus h would be starting at a once again and ending now at my value of x plus h. So I'm taking this larger area. Okay? Now, my question to you is, what do I get when I now subtract these two things? So if I were to subtract capital F of h minus f of x, I believe you're only going to get this small or thin wedge right here. Hopefully you can visualize and see that. Is that okay? Now, if we let this h value be really small, where have we seen that concept before? If we let h be really small, we can approximate the area of the region between x and x plus h, that's this, really the red region, using some sort of rectangle approximation. Because if you visualize this and it gets really, really small, that slanted piece up here really becomes almost like a straight line. So I'm saying if it's small enough, this shape actually approximates into a rectangle. And if I did that, then how would I figure out the area of f of x plus h? Well, that would just be the area of capital F of x, that blue section, plus the area from x to x plus h, which is now a rectangle. So this is now an approximate rectangle. And to find the area of a rectangle, it's the base times the height. The base, of course, is just the variable h. There's my base. And the height of this rectangle would be given by the actual y value. So the height would most likely be the y value. The y value is, of course, f of x. Does that make sense? Okay, so once again, this distance here is h, and then the approximate height for the y value, of course, is f of x. Now, you want the best approximation, right? Don't settle for okay, go for the best. So to get the best approximation for that tiny rectangle, which is, in this case, I'm talking about here, the second piece of the right-hand side from the above equation, you want the base to be as small as possible, meaning you want your width to be pretty much close to 0, or you want the limit, ooh, that concept again, the limit of h getting as close to 0 as possible. And therefore, when we do that, the height, once again, is just f of x. And so if we do that, let's see what happens. So once again, I'm going to copy this statement here first, down here, and then we're going to move it around and modify it. You're thinking, why are we doing this again? I'm going to try and show you how the capital f of x function is really the antiderivative, okay, of little f of x. So, in order for us to do this now, I want us to apply this idea of limit to the entire question. So it's now I'm going to say the limit as h approaches 0 of capital F of x plus h is also equal to now the limit of h approaches 0 of capital F of x plus the limit h approaches 0 h times f of x. Okay, we're going to take the limit of everything. Our next step now is to try to isolate. I want to isolate little f of x. So I'm going to take this and move it to the left-hand side. And if I do that, I'll get the limit as h approaches 0, capital F of x plus h, minus the limit of h approaches 0 of capital F of x. And I'm left here with the limit of h approaches 0 of h times f of x. Okay? Now our goal is to solve for f of x. So I'm going to actually take this limit of h approaches 0 with h and stick it on the other side as well. Here I'm multiplying by f of x, so the opposite of multiplication is division. So I'm going to now have f of x here, and then now I'm going to have the limit of h approaches 0. I'm only going to write it once, because I'm going to have the limit apply to everything here. And notice that h now becomes division, and here we go. What do you notice about the left side of the above equation? This is what again? That seems to be the definition of the derivative for capital F of x, right? So if I take the derivative of capital F of x, I get the original function f of x, which of course means that the derivative of f of x is, of capital F of x is equal to little f of x. And voila. There we have it. So the derivative of the capital F of x function, which is the area underneath the curve, is actually equal to the original function. And therefore, if we want to say it the opposite way, we can say that now capital F of x is now the opposite or the antiderivative of f of x. There you go. There is your proof. And now, hopefully you understand all this. You can now apply it to some questions.